In this section, we're going to discuss only one of the numerous case studies in the book. We're going to discuss how to convert hexadecimal digit to a decimal digit. The debugging section talked about this and used code, but didn't explain fully what we were doing. Hexadecimal is what's called base 16. That means it has 16 digits to represent numbers, 0 through F. After 0 through 9, we do A, B, C, D, E, F. We're all familiar with the decimal system, which has 10 digits, 0 through 9. Converting between number systems is a mathematical operation. When we program it, we usually take one digit at a time from the source, in this case hexadecimal, and convert it to target system, which would be decimal, and then multiply it by a certain value. And that certain value is the source base, 16, to some exponent. All of us have discussed polynomials in algebra. Until I really got into computer science and the math behind it, polynomials had no meaning. Now they have significant meaning. We have shortcuts in how we deal with numbers, and those shortcuts are misleading. For example, the number of days in a year is 365. The order of those digits is critical. We cannot say 653 and communicate the same value as 365. What it is that these are ordered based on exponents. The 3 is really 3 times 10 squared, or 300. The 6 is 6 times 10 to the first power, or 60, and 5 is 5 times 10 to the 0th power. Add those together and we come up with 365. Hexadecimal does the same, only the digits range from 0 to F, and their exponents would be the same. Each digit as we go from right to left, we'd start with 0, 1, 2. The base is 16. We would have 16 to the first power, 16 to the second, etc. That's all it is. Polynomials are the sum of those terms. The right-hand side at the bottom. The shorthand is on the left, 365. What we will do is we will take the leftmost hexadecimal digit and determine its exponent, convert that digit from hexadecimal to decimal, multiply it by 16 to the power of that exponent, and then add that to a variable that is keeping the sum of all the terms. My example at the bottom says 365 hexadecimal. So for example, 365 hexadecimal to decimal, we would take the length of the string representing the hexadecimal number, in this case 3. We would subtract 1 from it, because we have to count from 0 as indexes. We do that left to right. As exponents, we do it right to left. Index 0 is character 3, index 1, character 6, and index 2 is character 5. Exponents go in exact opposite order. The exponent for 3 would be 2. The exponent for 6 would be 1. The exponent for 5 would be 0. So the explanation says second digit is at index 1. 0, 1, counting to the left. And that would be its exponent also, because counting from the right, 0, 1, 6 would have an exponent of 1. The easiest way to figure that out is take the length of the string minus its index minus 1. So length 3 minus index of 6, index 1, 3 minus 1 is 2, and then subtract 1. 2 minus 1 is 1. That's its exponent. 3 times 16 to the first power. The code converted hexadecimal digits to uppercase. For programming, it's easier to convert them all to one case. That'll simplify testing. The normal digits, 0 to 9, will not change, but the letters A through F will change. But in the end, we will have 0 through 9 and A through F capital. The Unicode value of the digit 0 is 48. If we grab a character from the hexadecimal and it turns out to be between 0 and 9, we want to keep that digit. It has the same value in decimal as in hexadecimal. Each of those characters is encoded in Unicode, 0 being the value 48. 48 and 0 are not the same thing. So what we do is we take the Unicode value of the digit and subtract from it the value 48. That makes 48 minus 48 for the digit 0. And that's exactly the result of 48 minus 48. 0. For 9, we would have 57, subtract 48, and we come up with the value 9. In a different sequence are the capital letters A through F. Their Unicode range is 65 through 70. So what we would do there is subtract the letter A from those, so that if we had the character A, which would be encoded as 65, we would subtract from it the value of the letter capital A, 65, and come up with a 0. A represents decimal 10. We don't want 0, we want 10. So after that subtraction, we add 10, because A through F represents the values 10 through 15. We use the same trick of subtracting the first digit from whatever the character is, but then we have to add 10. In the end, by doing these two different ranges, we will come up with an integer in the range 0 to 15. In our selection logic, we have three different options that we must consider. That is, the character from hexadecimal is a digit, which means it translates directly to decimal. The second case is the character is A through F. That's not going to have a direct correspondence to a decimal digit. So we have to do the subtraction and then add 10. And the third and final option is character is neither, and we have to handle that by issuing an error message, terminating the program, or some action. We don't want to try to convert something that is not a legitimate hexadecimal character. I've explained this math. Here's a quick review of it. For example, the digit 7, Unicode value 55. We subtract the Unicode value of the digit 0, and we come up with 7. Assuming letter B, which is decimal, the equivalent's 11, it is encoded as value 66. The capital letter A has Unicode value 65. We subtract that from 66, answer 1. We add 10, result 11. B converts to decimal value 11.